Thank you for the introduction. So I'm Thomas Châtelet, and my talk is about near-field thermophotonic cooling, accounting for drift-diffusion. My supervisors are Pierre-Olivier Chapuis and Olivier Mercier. And let's begin. So, yes, I like it. Okay. Sorry. Now it's working, of course. Okay, so first I'll give you a small introduction regarding near-field thermophotonics. Then I'll go on the detailed balance approach to see the cooling power that we can obtain with this framework. Then I go to cooling power performances with a more accurate electrical model. And then I will talk about solid-state cooling in general, or more precisely on thermophotonic cooling versus thermoelectric cooling. And then I'll go to the conclusion and the next steps. So first, what are near-field thermophotonics? Let's say that I have a cold reservoir at temperature Tc, that I have a hot reservoir at temperature Th, and I have an LED affixed on the cold reservoir. Let's give this LED some electrical power, and what I obtain is electroluminescent radiation. Now, because the energy of this electroluminescent radiation is superior than the electrical power that we set as an input, well, we have some cooling power. Because we have a temperature difference in between the two reservoirs, I have some thermal radiation here. So basically, how does it work? We can have some cooling because we are able to pump heat from the LED crystalline lattice. So basically, LEDs can be used as a heat pump. Okay, one way of improving such a system is to have a second thermodynamic engine, a PV cell, on top of the hot reservoir. What will it do? It will convert some of the electroluminescent radiation to electricity, and it will be able to feed it back to the LED, thus reducing the amount of power that we need as an input. So this is thermophotonic, but I talked about near-field thermophotonics. So when the distance between the LED and the PV cell is greater than the beam wavelength, well, only propagative modes are exchanged, and basically it means that this KI parallel, which is a projection of the wave vector on the surface of one of the two emitters, is lower than the wavelength in vacuum. When we reduce the distance between the LED and the PV cell, additional nodes are exchanged, and we have a greater number of modes that are exchanged in the system. So N, of course, here is the refractive index. So basically, we can use near-field effects to increase electroluminescent radiation, which will boost our cooling power, but because we diminish also the distance, we have some increase of this thermal radiation that will, in fine, damage our cooling power. So those are near-field thermophotonics. And okay, to have an overview of what are those thermal radiation, well, let's say that I have an LED at 210 Kelvin. I have a PV cell at 300 Kelvin. LED is made of gallium arsenide. PV cell is made of aluminum gallium arsenide. The aluminum fraction is set so that it matches the band gap energy of the LED here. And if we look at this thermal radiation, well, this is what we have here. The monochromatic flux with respect to the angular frequency here. We have the propagative modes that are here. And as you can see, those are several orders of magnitude lower than those evanescence modes contribution. So here, this is a double logarithmic scale. And here, when it is positive, I consider that there is some heating of the LED. Okay, so keep in mind that our PV cell is biased here. If I bias my LED at 0.3, so lower than the PV cell, well, I have some electroluminescent radiation going from the PV cell to the LED. So this is not what we want. What we want to do is some cooling. So I have to increase the bias applied to the LED. And, well, when we have the integration of this electroluminescent peak being superior to the integration of this thermal radiation, well, we have one condition in which we can have some cooling power. But we also have to take into account this electrical part here. So how do we do this? So using the detail balance approach, okay, so this is the cooling power. We have the electroluminescent peak integration, thermal radiation integration, in here, the LED input power, and we can say that it is basically I supply to the LED times current density times this. This is the power we set in the LED. And, okay, in the detail balance model, well, in an ideal case, the current density, we can compute it with E times the integral from the gap of frequency to infinity of the net photon flux. But our world is not ideal, and we can also take into account this term here that will account for non-idealities thanks to this IQE thing here, and the IQE is the internal quantum efficiency. So it's the number of radiative recombination divided by all the possible recombinations. Radiative recombination is basically, I think everyone in this audience knows that, okay, recombination of electron hole pair give birth to a photon, and vice versa. And non-radiative recombination is the opposite. Electron hole pairs do not create a photon, and vice versa. So thanks to this electrical model, we can set the upper bounds of, for the cooling performances of the TPX system. So, let's say that I want to study the effect of gas size in the thermophotonic cooling engine. So here, I set the temperature of the LED to 290 Kelvin, temperature of the PV cell to 300 Kelvin, cooling power is expressed again here, and in order to have a full overview of the system, I can also set the coefficient of performance. So basically, coefficient of performance here is output versus input ratio, so it's cooling power divided by the whole power given to the system, and to see how close we are to ideal situation, we can use the Carnot efficiency that is displayed here, and if we divide the coefficient of performance divided by the Carnot, well, we have the scale coefficient performance, and this gives us how close we can get to ideal conditions, reversible thermodynamic engine. So here you have the coefficient of performance with respect to the cooling power for several gas sizes. First thing that you can see here is that if I put the bias of my PV cell to 0, well, I have almost zero coefficient of performance. But I don't have such a degradation of the cooling power. So this means that if we want the system to be more sustainable, to be more energy efficient, well, we have some interest in putting some bias in the PV cell. Also, you can see that if we increase the gap size from 10 nanometer to 10 microns, we have a 1 order of magnitude drop of the cooling power. And here, you can see that if we decrease the gap size from 10 nanometer to 10 micron, well, we can multiply our coefficient of performance by 4, but we won't be able to cool as much anymore. So this is expected. So basically, there's a trade-off between the coefficient of performance and the cooling power. So if we want to get better cooling, well, we have to aim for smaller gap size, which will diminish the cup that we get today. And if we want to have better efficiency, well, we can try to get some higher distance. But what I want you to keep in mind is that we here have this thermal radiation. What happens if we don't take it into account? Let's say that we can manage to put it at a lower level, like 0. What we obtain is this. It means that, okay, I have a small increase of the cooling power, but I can almost reach Carnot for 0, but it also means that there are some more possibilities for our system to have some even better coefficient of performances. So, the staple point here is to say that, well, if we manage to have some lower thermal radiation, we can have a slightly better cooling power, but we can also have a really bigger coefficient of performance. Okay, so we studied the gap size, we studied the PV cell LED temperature, PV cell temperature difference, but I talked earlier about the IQE. How does it go in our system? So, I put it again here, and this is what we obtain if we reduce the IQE from 100% to 95%. You can see that the cooling power is divided by a factor 66, and yeah, this is very big. And we can see also that the coefficient of performance is divided by a factor 100. So, IQE is the second major bottleneck of the system. And here, IQE, in the detailed balance approach, is a value that we set as an input. But there's a way to account for it more accurately, using the drift-diffusion model. So, it will be a bit convoluted. I hope you will follow me. So we use, there are two blocks, the radiative calculations and the electrical calculations, all right? So here, this is we compute the photon flux, we compute the radiative heat flux, and in the radiative heat flux, we use a chemical potential that is E times the bias applied to one object, so LED or PV cell. And we plug those numbers into the electrical computation. So this is the drift-diffusion model in the Boltzmann approximation. So we have the continuity equation. So if we take the space derivative of the current density equals to E times this derivative of the photon flux, that depends on mu, that is here, and we subtract the Auger and SRH and surface recombinations. So those are subject to the electrical carrier concentrations. So continuity, then, well, drift-diffusion equation. So this is the current density of electrons on holes, or holes. So this is the conductivity times the electrical field. So this is for the drift part, and for the diffusion part, we have E times the diffusion coefficient times the derivative, the space derivative of electron density. And then we use Poisson equation to get the electric field. And we apply weights, and this is in derivative scheme. So we iterate to get those quantities, and then, well, we have to, we feed it back to the whole radiative block. So we get a new chemical potential that we already use here. And, well, we go all over again. And, well, once we have converged, we have the current densities, we have the carrier, the electrical carrier densities, and the electric field. And this code has been developed by Julien Lejeune, and I tuned it so that we can have convergences for the system I use. So, now that we have established what is the drift-diffusion model, we can use something that is more real. This is a structure that is a simplification of the structure that we have in our project. So this is an LED made out of gallium arsenide for the intrinsic region, sandwiched in gap, gallium phosphide. And then we have perfect mirrors at the back of the two. And here we have a fraction of aluminum that is put so that it matches the gap of the gallium arsenide here for the intrinsic region. The distance between the two is called D again. And this is, of course, a heterojunction. And previously, Mr. Perez has given us the homojunction thing. Okay. So, this is the cooling power that we can obtain with respect to gas size. So, for now, the results I present here is for zero biased PV cell. In plane lines, what you have is the cooling power with a non-zero thermoradiation, and for dashed lines, what you have is the cooling power with zero thermoradiation. So what does it mean in other words? It means that we don't take frequencies that are below the band gap when we are having this situation, and it means that, well, this section here is forbidden because we have too big thermoradiation. Also, you can see that the order of magnitude that we can obtain for almost zero temperature difference is 2 orders of magnitude lower than the result I previously showed you. And you can see that, well, we have 1 order of magnitude increase of the cooling power thanks to near field effects, but we have to tune it so that this thermoradiation is not damaging our cooling power, so there's a local maximum that is being displaced around here. Okay. So you will tell me, yes, but Thomas, you know, because we are French here. But you know that you told us about the detailed balance approach, you tell us about the drift-diffusion approach. Can you compare the two? Of course, we can do it. If it wants. Okay. Okay. So on top here you have the detailed balance approach results, and on the bottom you have the drift-diffusion approach results. So here in plain lines you have with non-zero thermal radiation, and here you have a small difference. This is due to the fact that here thermal radiation is damaging our cooling power. And you have a 2 orders of magnitude drop of the cooling power in between the results obtained in the two components of the system. And of course, well, the colors matches, so that's okay. Here we have 270 Kelvin, and here the same. Main message is, well, you have a tendency, a decrease in the far field here, contrary to what we had here. So this is why we need to set the IQE not as an input parameter, but something that we have to compute. And, well, for just a 30 Kelvin temperature difference, it's beginning to struggle cooling something. Huh? Okay, so why is this discrepancy here? Why is this not constant like on top? Well, let's first look at the temperature difference, the effect of temperature difference on the system in the LED. So here you have the IQE with respect to the LED bias for several LED temperatures. So when we lower the temperature in this transition here regime, you can see that there is a decrease of the IQE with temperature. Even though in the literature, okay, we know that if we decrease the LED temperature, we have some more radiative recognition, so we expect the IQE to go up. But you can see also that here, there's a point in which we barely reach 93% IQ. And if we compare this graph, so each curve corresponds to each curve here for the cooling power with respect to bias applied to the LED. And as you can see here, just a 30 Kelvin, additional 30 Kelvin difference in between the LED and the PV cell will divide by 2 our cooling power. So there's the slight decrease of IQE with the temperature difference will induce a strong reduction of the cooling power. But what about the gap size? So here is the IQE with respect to the LED bias. So the darker the curve, the narrower is the distance between the LED and the PV cell. And as you can see here, well, when we go from bottom to top, it means that in the 200 nanometer we reach 93%. Yep. And then we can almost reach 1, but you can see here that there is some shift of the IQE. Also here we have I de-zoomed this graph so that you can see that below 4.8 volts, well, the IQE is so low that you can't expect to have any cooling going on. Okay. So you have here a small IQE for 220 nanometer, and here you have a rather high IQE for 20 nanometer. You obtain this cooling power. So, okay, I'll do this again so that you can see that the distance is decreasing in this direction. It means that in purple, well, here you have a whole region in which you can't have some cooling. This phenomenon happens because you have a really low IQE. If you decrease to the distance between the LED and the PV cell to 20 nanometer, you can see that there's also a region here in which, well, there's no cooling. But why is that? I have an IQE here that is big. Normally I should have some cooling. And this is due to the fact that the thermal radiation will damage our system so much that you won't be able to have some cooling. So in this graph, you can see that there are the two bottlenecks of my system, thermal radiation and IQE. All right, so now that we have said that, we've also seen some things that you are already aware, but we wanted to see. So I shifted the barrier doping concentrations in the in-gap part here in the LED, and as you can see, as we increase the barrier doping, we have some better cooling power, and this is due to the fact that by increasing barrier doping, we decrease the difference between the bias we feed to the LED and the bias that is seen by the LED, thus resulting in better cooling performances. Okay, so we had some detailed balance results, we had some thermophotonic cooling results. How do we compare with literature? So this, again, is a bit convoluted. So in colors is the defects that are taken into account in the literature. And in shapes, you have the type of the emitter. As you can see, when we go from here top to bottom, well, we increase the band gap energy from top to bottom. So something that is in our article that I won't explain here, but okay, I can answer some questions about that, is that when you increase the gap energy, well, you have an increase of the cooling power. Thus, this is why indium arsenide made LEDs have some lower cooling performances than, for example, cadmium telluride here. Okay, you can also see other things. So our results are here in curves, and you can see that for the detailed balance here at a 0 temperature difference, we are here. And by just increasing it to 30 Kelvin, well, we have this drop here. So it's really a thing. And you can also see that for a 0 temperature difference in a drift diffusion, we are here. Why is it important? Because if you look at the black stars here, it represents the thermoelectric cooling devices. And what we want to show you is that, theoretically, thermophotonic cooling devices can rival the penalty modules that are here. Okay. Well, I guess it's my time, so let's move on. We have studied the cooling power of a TPX device. The near-field effects contribute to a factor 10 for better cooling power. And we have identified the two bottlenecks of our system. Thermoradiation. If we have a too low gap size, we will increase dramatically the thermoradiation, thus reducing the cooling power. And if we have an IQE lower than 90%, well, don't expect some cooling. And also, we have said that, theoretically, near-field thermophotonic cooling could rival with thermoelectric cooling technologies. For the next test, even though I'm at the end of my PhD, well, we try to aim to get some non-zero PV bias to get some cup steady. And we want to get to make this a whole more realistic structure converge to get better some better IQM1 port and to have some better experimental matching results with our collaborators in the project. So this is for the IQ bottleneck, but what about this thermoradiation bottleneck? Well, we have used the mesh code to structure the surface of the LED and try to reduce this thermoradiation thing. So if you want to get back to it, I have some slides also. And we have validated this code with some results of the literature. And, well, in fine, what we want to do is to reduce the photon polariton contribution, so which is the main contributor. But let's say that we want to shape the surface of the LED so that we can reduce a specific wavelength in which we have some great contribution of the thermal radiation. And for the experimental results, well, you have Mathieu Thomas and Wissam Gale just behind here, and they will talk to you about what we can obtain experimentally. Thank you for your attention. My article is here, my LinkedIn is here.